All right, so this section we're talking about transformations. I don't think it's a hard topic. I think it's a quite pretty easy topic. You can tell me what you think about it down below. But to go along with this, I made a little Desmos thing. So I think it would be useful if you followed along with it. I posted in the Discord if you want to pull it up while you watch. So let's think about what's happening here. Use the graph of f of x equals x squared to obtain the graph of g of x equals x squared plus 3. So let's think here just for a second about what's happening. If we're not going to take so long with the other problems, but we will on this one. The process is simple, but I do want you to see what's happening. So if we think about for our f function here, and we just think about some different values. So like if x is negative 2, we get positive 4, negative 1, positive 1, 0, 0, 1, 1, 2, 4. Right? But then now what's going to happen with the g of x? So just think about how, like when we plug in these values into the g of x function, well, what's going to happen? We're going to do the same thing that we did with the f function first, right? We're going to square it. But then we're going to add 3. So basically, we're going to get all the same, these numbers over here, but then we're going to add 3 to them. So you get 4 plus 3 is 7, 1 plus 3 is 4, 0 plus 3 is 3, 1 plus 3 is 4, 4 plus 3 is 7. And so those are the points on the new graph. But what really happened here? All the y values just went up by 3. Which makes sense, right? Because of everything we talked about. And so I just want us to be able to see this on Desmos about how that's working. So look at how the plus 3, that's just like this b that's on the outside of everything. And if you change that b, that's making the graph go up and down. When b goes up, the graph goes up. When b goes down, the graph goes down. And so that's just to show that's what it's doing whenever you have a number on the outside. See there, it's plus 0.8. That means it's 0.8 up, the y value. If it's negative 4, that means it's negative 4 down. Again, the y value, because it's talking about up and down. And that's just the gist with this whole different thing today. You have all these different numbers that you can put in the different places of equations, and you can see how it affects them. If you have a number on the outside, you call it a shift. You call it a vertical shift. It shifts the graph up and down. This one is just down, right? X squared minus 4. So that's just, you can know really quickly. I guess maybe we should reset some of these. So C should be 1 and D should be 1. And A, the number on the inside, should be 0. C should be, in this case, negative 4. You see it's just a plain parabola, just down 4. No, C shouldn't be negative 4. Come on, C should be 1. A should be 0. B should be negative 4. There you go. Just a parabola down 4. Because everything is normal. Look and appreciate for a second when we put those numbers into the equation. So D is 1. That's 1 times. So it just doesn't matter. C is 1. That's 1 times. So it just doesn't matter. And then X plus A, which is 0. X plus 0. So it just doesn't matter. So this is saying just the B. You can see what happens just with the b. It's just moving that graph up and down. So the one we had before, x squared plus 3, it's just right here. The normal, x squared plus 0, is just right here in the middle. And then the one they're talking about here, x squared minus 4, that's just down at minus 4. And that's really as simple as transformations are. It's just shifting the graph around. So we're not going to write everything, write something for everything necessarily. So see how this one is different, right? It's not x squared minus 2 in the style that it's been before. We would know how to do that. That would just move the graph down 2. But see, this is different. This is x minus 2 squared. So if you look up here at the equation I built, see how that's the negative, that's the a. That's the a in the middle. So if we wanted to do this on the graph, we would want to make that 0 first. You see, that's just our plane parabola. But let's not do it on the graph just yet. Let's go to the table and think about it. So let's again, like before, I guess we can just copy this graph. Because this is still our original function that we're using. And what is happening here? So here, when we plug in an x value, so like when we start, if we plug in x equals 0, well, what's going to happen? If we plug in x equals 0 into this function, the very first thing that happens is that we have 0 minus 2. So we have minus 2. And then we're squaring it. So see how when we plug in 0 into our g equation, it's the same as plugging in negative 2 into our f equation. So when we plug in 0 here, we're going to get 4. And then when we plug in x equals 1 into this equation, see how when we plug in x equals 1, 1 minus 2 is negative 1. It's like we were plugging in negative 1. So when we plug in 1, we're getting 1. And similarly, look at the actual pattern. We end up adding 2 to all of the different x values. So if we continue that, this is 2 and 0, 3 and 1, 4 and 4. So what is this going to do? Well, we're adding 2 to all the x values. So that should just move it 2 in the positive direction. So if we make this a negative 2, it moves it in the positive direction. So notice how this is different. When we make this number bigger, this number on the inside of the parentheses here, this a value, if we're looking on Desmos, when we make it bigger, the graph goes to the negative side. And when we make it smaller, the graph goes to the positive side. And you're going to find that that's always the case with x. And so when you're doing transformations, you can just remember that. X is always opposite. So when it's like, when here you're adding something, if it's like a plus 7, that means you're going negative 7. I guess I changed it to negative 6.8 in the negative direction. But if a was negative, you would then be on the positive side. X is always opposite. Now, the reason x is always opposite is just because the way I think about it is things are being directly done to it. Like, look how this minus 4.4 here, it's being directly done to the x, which is different than that plus b that we looked at originally, right? Because this plus b, this b value that affected the y value, where if we made b go up, the y values went up. If we made b get smaller, the y values got smaller. It's not being done directly to the y, right? And we could see that if we did think about this being done directly to the y, then it would be opposite. Oh, Desmos isn't going to work for us like that. That's okay. But just know that if we did do it directly to the y, it would be opposite. And the reason would be because we have to subtract it to the other side. Because then it would be like y minus b on the other side. And then it would be opposite, just like the x. So what we can know with transformations, but really just because the way we write our functions, is if it's being done directly to the x, then it's always opposite. If it's not being done directly to the x, that means it affects the y variables, and it's not opposite. I feel like I might have said that wrong. When it does affect the x, it is opposite. When it does not affect the x, it is not opposite. What they'll say is that y is intuitive and x is counterintuitive. So look, here we just have another example. So this, what do we even want to look at here? Do we ever look at that on Desmos? So we need to make b 0 again. And a, so before, this one they wanted it to be negative 2. And we saw that it went 2 on the positive side. For this next one, they want us to make it positive 4. And we see that it goes 4 on the negative side. And that's the whole opposites idea that we just talked about. But then look at this one. This one's just doing both of them. So if we sketched it on paper, which is often what you'll be made to do in class, unfortunately, is you just do them both at the same time. So you got x plus 3. That's being done directly to the x. So that means you're going side to side, and you're going to the left. So left 3, and then down 5, because that's on the outside. So that's right here. And then you just have to know what type of graph you're doing. This is still an x squared graph. So then from there, we just have an x squared graph. And you can do it perfectly if you want. Not necessary. You can see how I've been doing so badly recently. But that's just your normal parabola there. And that's why I think it's just so much nicer and so much, what do you call it, practical to use a graphing calculator. Because anytime in real life you're just going to use a graphing calculator. If you need specific numbers, you shouldn't worry about getting specific numbers. If you want to sketch, you just want the shape. You should get the parts you cared about. If I cared about the x-intercept, then I would more specifically find the x-intercept. But I don't. I just wanted, really here, when you give transformations, you just want that main point mainly. And if you want a specific graph, specific point on the graph, you should just go to the graph anyway. That's another beef I have with transformations. Alright, so this is a different type, right? Because here you're not adding or subtracting, you're multiplying. So what is that going to do? We actually have all those pre-programmed. So see how that 2 is on the outside of the function. So that means it's affecting the d value. So let's reset these to b is 0 and a is 0. So we're again just looking at a plain parabola. Oh, except for they don't want the plain parabola here, do they? They want an absolute value graph. It'll be similar though, so we can still use this. But see how it's the number on the outside. It's the d value that they want. And really the same way that when we added a number on the outside, we just added to the y values. When we have a number multiplying on the outside, we're just going to multiply to the y values. So all of the y values of the original function, they're just going to get twice as high. So think about how that's going to work. That's just going to stretch the graph up. And again, we can see, because Desmos is so beautiful with this, we can stretch it up or make it negative and stretch it down. So that's what the number on the outside multiplies. You make it bigger. See how the bigger and taller and skinnier it gets? The smaller, the closer to 0, the shorter and wider it gets. And then once it hits 0 and goes negative, it just flips over. So I think, I don't know, Desmos just makes it so clear. I think this is Desmos at its peak, is with transformations. So that would work the same with the absolute value graph. I guess we could come down here and look. If we have the absolute value graph, there's our absolute value graph. If we can just even throw on the d. So if we did d, absolute value of x, you see that's making it shorter and taller. So when d equals 1, it's just the plain absolute value graph. When d goes up, it becomes taller and skinnier. Still the same shape, still the same absolute value graph, just taller and skinnier. And then when it gets closer and closer to 0, it gets flatter and flatter, absolute value graph. Until it hits 0 and it's totally flat, and then it goes to the other side. And so that's with the negatives too. I'm sure we'll talk about negatives in a second. But that's how the negatives work. And so here, see here, this is the smaller than 0. So they're thinking when we made d2, it made it steeper and taller and skinnier. Like we said, we're multiplying the y values, so it's becoming taller and skinnier. And then if we multiply by a fraction, though, if you multiply by a fraction, you make something smaller, right? So all the y values are becoming smaller. All the y values are halving as opposed to doubling. So you see how it becomes smaller. Ooh, what is this? Graph. Ooh, they gave us graphs in the figures. Hold on, we gotta pause. We gotta get the pictures. Okay, so this is a fair use for transformations. Because here, if we don't have the equation, if we just have a graph, and we want to transform the graph. So you see here, they give us the graph of f of x, and they want us to find these two other graphs. So I'll just try to do it right on that picture. And let's just think about what these are doing. So with A, that's like what we just did, right? It's got a 2 on the outside. So that multiplies all the y values by 2. That doubles all of the y values. And so if we just sketch it out, Remember when we have these points, these aren't the only points on the graph, but those are going to be good guide points for us because they're going to go twice as high, twice as up, and twice as down. And now 0, remember it really is you're multiplying the values by 2. So here where it's 0, you're going to multiply by 2 and it's going to stay 0. So basically this graph, it's going to be exactly the same. It's just going to go twice as high, like I said. Because you're multiplying by 2 on the outside. So when you multiply by 2 on the outside, it affects the height. It's going to make it taller. Now here, this 3, here, let's do this. Let's bring this graph off to the side now that we have it. Maybe I'll put them back on at the end. So let's do this in pink. So this 3 is on the inside, right? And what did we say about stuff being on the inside? Is that it's always opposite. So in this case, just like with the y, we think about multiplying and make it bigger, dividing and make it smaller, but it's actually opposite because it's with the x values. So here we're multiplying by 3, so that means we're actually going to be dividing. We're going to be dividing all of the x values by 3. So that's going to be tough to show, especially because the graph's not really separated for it. But we could try to do some specific values. So if we divide by 3, so if we think this 0, again 0 divided by 3 is going to stay at 0. But this is now, instead of being at pi, it's going to be at pi over 3. So I'm maybe just going to estimate where that's going to be. And then, let's see. Is that not even a good estimate? Because what do I know? Trying to just use good points here to be better about it. So 3 pi over 2, when you divide that by 3, you just get pi over 2. So this bottom point here, that should be here. Yeah. It should hit -1 at pi over 2 because you're dividing everything by 3. And then over here at 3 pi, where it gets back down to 0, that should be like that. And I think the rest I almost just have to eyeball. So guess just something like this. It's going to bottom out there, and it's going to have to go back up and then back down. So you see how the height is not at all affected, just the width. All of the x values are being divided in by 3. It's making it narrow, or it's squeezing it all in. Okay. Next, we already talked about this. If you multiply everything by a negative, it's just going to flip the graph over. That's like the easiest thing to see on Desmos. I don't even need anything special for that. You just graph your x squared, pop a negative in front of it, turns it upside down. Does that with every graph. Any crazy graph, no matter what it is, if you throw a negative in front of it, it's going to turn it upside down. It's kind of a beautiful thing. Now, if you put a negative on the inside of it, think about everything we've done so far. It actually follows the same rule. This negative is on the outside. It's not being done directly to the x, so it's talking about up and down. Whereas this one is being done directly to the x, so it's talking about going back and forth. Now, how we said everything with an x is negative, or is opposite, you can't really have the opposite of a negative. Because opposite kind of means negative. So you don't worry about that. You can think about multiplying versus dividing by a negative if you'd like to, because that's really what this is. We're multiplying by a negative. But you multiply by a negative, divided by a negative, it's the same thing. So you don't think about the counterintuitiveness for the negatives. You just know if it's on the inside, it's done to the x, which means it's going side to side if it's directly on the x, and if it's not done directly to the x, it's talking about up and down. And now, how do you not know that this one in particular is directly to the x? Because remember, at least I know that's one of the things my elementary teachers always harped on, is that those parentheses make a difference. Negative x squared is different than negative x squared, because the one on the left is negative x times negative x, which is positive x. The one on the right is just x times x, and then you make it negative. Those things are not the same. So how it's written, that's on the outside, and it's being done to the y values. This one, like we said, is on the inside. It's being done to the x values. So it's going to flip it sideways. So what does the graph of this look like? This is one of the graphs we need to know. I guess maybe at the end we can go through all the different graphs that we got to know. This is the square root graph. The way to know the square root graph, I guess we get perfect points. I got that one. Did not get that one. And the last one. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Did not get that one. So that's what the square root graph looks like. It's the top half of a parabola, which makes sense. This is not what they graphed. We just graphed the square root of x. But it makes sense that it's the top half of a parabola because if you square both sides, you get x equals y squared. So you see how that's like a parabola with y. But if you square root both sides and don't include the plus minus, then you only get the positive part, which is what the square root is. So that's the square root graph. We can see it perfectly over here. Let's close everything else. We got our square root graph there. And if we make it negative, like we said, the negatives, they flip it, but it's on the inside. So it flips it side to side. It flips it over. So this graph, I guess since we sketched that one, we should graph the actual answer. It's going to be the same thing, just flipped over the y-axis. Alright, so now we're writing an equation for it. They want us to do that transformation. So we'll have that the function is equal. So we're using the absolute value. They want us to shift it 2 units to the left. So left and right, that means it's the inside. Left is negative, but everything on the x is counterintuitive and opposite, so we want to add, right? So that should be the absolute value of x plus 2. And then shifted 3 units up. So that's just on the outside. Shifted up 3. And then reflect it over the y-axis. So then we got to have a negative on the outside. So this is a little unclear to me. So are they saying, and I don't think there's a correct answer to this necessarily, but are they saying we're going to shift it to the left and up so that it's here, and then we're going to flip that entire thing over the y-axis? Or they say they're just going to do a vertical flip? Because when I think about these, I think about them just being in place. Like if you're just going to do a vertical flip, because I guess they're probably thinking about order. That's why they say like finally graphed. So if you're reflecting it about the y-axis, I think you got to do it to the whole thing if you're going to be thinking about it like that. Because if you just have this negative out in front, that's just going to flip it in place. That's not going to flip it over the entire y-axis. If you want to flip it over the entire y-axis, you're going to have to multiply that negative by everything. Let's look at on Desmos to just confirm that. So if we've got, let's turn that off. So we're looking at the absolute value of x. Well, let's graph this equation. So the absolute value of x plus 2 plus 3. So right, see that's your to the left and up. And if we put a negative on the outside, see how it doesn't flip it over the y-axis. So this is how I like to think about it. I like to think about it like that, where it just stays in place and it flips. But they are saying it would have to. They want it to flip over the y-axis. So see, when you add parentheses, when you do a negative to the entire equation, it flips it over the y-axis. If you just do it to the part before you add, it just flips it in place. So it just depends on what you're going for. Oh, they're thinking about more. So this is a different parent function. It's not so clear to see. But this is a parent function. It's the parent function y over x. And they're just doing transformations on it. So if we wanted to graph it, let's go ahead and sketch a graph. So what does the parent function y over x look like? It's one of the ones that you need to know. It looks, change colors, looks like this. And this. But then what are they doing? So actually, before we even go on, the key part of this graph is the asymptotes, right? You think about if y equals x, x is never going to be able to be 0, but also y is never going to be 0, because 1 divided by any number is never going to get you 0. So this graph has two asymptotes. And when you're thinking about doing transformations with this graph, those asymptotes are key. So let's switch to green. And so what is this telling us? Well, we're going x minus 2. It's counterintuitive. So 2 in the positive direction for the x values. So our asymptote, you start with the asymptote. So we're going to move our asymptote 2 to the right. And then we have this plus 1. That affects the y value. So that's moving the other asymptote up 1. And so take a second to appreciate that if like our asymptote that's like this, if we move it up, that doesn't do anything because it's just a vertical line. So that's why we didn't care when we thought about how we moved it up. And then this one, when we moved it side to side, we didn't care, because if we take a horizontal line and move it side to side, it doesn't change. And then the 3, so that's like on the outside, right? Because it's not down there with the x. So that means it's making everything taller, stretching it up. So think about stretching it away from the corner compared to the last one. It's harder to show that. The biggest thing about when you graph these is your asymptotes, is that you show that you moved the asymptotes properly. But the stretch is not going to affect the asymptotes. But look how these asymptotes, how we sketched them, it's very clear. We moved it 2 to the right and 1 up. And I'm not too worried about specific points because, again, if we want specific points, we'll just go to the graphing calculator, which we will do. But now domain and range. So that's just the asymptotes, right? Kind of remember the asymptotes is where the graph never is. So, and you can see it just from the equation, that our domain is that x can be anything, but x cannot be 2, because then we get 0 in the denominator. And we can see from our graph, with our horizontal asymptote at 1, that y is never going to be 1. Y can be anything, the range is anything, but not 1. And the domain is anything, but not 2, because those are just the two asymptotes that we have. So right, let's go to Desmos. Let's just start a new graph. So we've got 1 over x. There we go. That's our parent function. It's beautiful. So, of course, Desmos doesn't show the asymptotes, but it doesn't need to because it's already perfect. So x minus 2, it can just actually approach the asymptote flawlessly because it's a computer. And then plus 1. So see how it went up. See how that asymptote is obviously up 1 and over 2. We can graph them if we want. X equals 2. There's that asymptote. And y equals 1. There's that asymptote. So very nice. All right, so the next one's a bit of a doozy, at least for how I'm going to tell you to do it. So first off, I want to rearrange this because this is ridiculous to have x second. So remember how we talked about the negative on the outside will reflect it over the whole axis, but the negative to the entire thing will just flip it in place? Well, it's the opposite for x, which makes sense because x is opposite. So I don't prefer to look at it like this. I'll tell you how. If you're going to look at it like this, this is what happens. So you move it up 2, and you move it 1 in the negative direction, right? So that's the graph of the square root of x plus 1 plus 2. And then to apply the negative, you flip it over the entire x-axis, or y-axis, which I just think is harder to see. So then you would do that, and that would be your final answer. But I just think that's harder to see than the way that I would show you how to do it, which is if you have a negative on the x, or frankly, any number at all on the x, you should factor it out. So we should rewrite this as the square root of negative x minus 1. And what that shows us is that we're going to do the minus 1 and the plus 2, which moves it 1 in the positive direction, 2 in the positive direction. But when we have everything factored out here, then it's not like over the x-axis thing. It's just in spot, in place. So now we're just going to take this graph and just flip it in place, not over the x-axis. And I've always liked that better. That's always how I've preferred to look at transformations. So let's look at Desmos to just confirm that. So What are we graphing? The square root of 1 minus x plus 2. Right. See how that's the graph. So that can be pretty confusing because it is originally a plus 1, but it's on the positive side because of that negative. So you've got the two different ways to think about it. A lot of teachers do this first way, where they talk about like a specific order you need to do it in, but really the order you do it in doesn't matter if you have it factored properly. So whatever's on the x, you have to factor out. Whatever's on the y, you've got to not factor out. That's basically how it goes. And then what's the domain and range? Well, now that we know the graph, that's really going to be the best way to think about it is just the graph. So especially for the range. The range, you really always need the graph. So the range tells us, just look at where the graph starts. The graph starts here at 2 and then just goes up. So the range is just anything from 2 to up. I guess it can be 2. It does start there at 2, so we'll put a bracket on 2. So that's the range. And I mean, the domain we can get easy enough from the graph. We can just see that the graph starts there at 1, but then goes backwards. It goes negative. So we'd say that it goes from negative infinity up to 1. And again, it can be 1. And why does that make sense that it's negative? Because we all know that you can't have negatives in a square root generally. Well, because look at what happens. If we take what's inside the square root and we say that it has to be greater than or equal to 0, when we end up solving for x, remember that when we divide by this negative, we're going to have to flip the sign. We'll get x is less than or equal to 1, which is the same thing we said for our domain down here. So that just confirms it. Oh, wow, and that was the end of it. Only 30 minutes. That's not bad. So transformations. Yeah, I mean, they're pretty simple. They're just there to help you like picture graphs in your head. So what's the summary? Anything done on the outside affects up and down. Anything done on the inside affects side to side. Anything done on the inside is always the opposite operation from what you'd expect. And if you add or subtract, that just shifts it. That slides it side to side or slides it up and down. Doesn't change the shape. If you multiply or divide, when you multiply, it's going to make it, you think about stretching it, making it bigger, either stretching it up or stretching it sideways. And if you're dividing, you think about squeezing it down or squeezing it in. Of course, with the x, it's opposite. So with your dividing on the x, you're actually stretching it. And when you're multiplying on the x, you're actually squeezing it. But just because they're opposite. And then what else? Negatives flip. I guess the last thing is just what graphs do we need to know? So that's always going to depend on your teacher. I would say, what do we need to know? We need to know the plane x graph. Of course, y equals x. You got to know y equals x. You got to know x squared. Of course, we talked about that today. You got to know x cubed. For sure. Some teachers, I would say that you needed to know x to the fourth. Now, what's the key difference between x to the fourth and x squared? So I would say x to the fourth is flatter in the middle, but then steeper on the outsides. Or yeah, steeper out. Yeah, and by outsides, I mean outside 1 and negative 1. So you see inside 1 and negative 1, it's flat. Outside 1 and negative 1, it's steeper. And that relationship actually just gets bigger and bigger the more bigger you make that number. As long as it's even. Because if it's odd, then it does like an x cubed thing. But actually, you can see that pattern continues if you compare x cubed to x to the fifth. X to the fifth is just flatter. But I didn't make them necessarily memorize x to the fifth. But you had to definitely know x to the fourth. X cubed, x squared. And then just some of the other ones we talked about today. You definitely have to know absolute value of x. That's your v. You definitely have to know the square root of x. We used that one today too. You definitely have to know... Well, no, you don't definitely. I included this one. I know a lot of other teachers will as well. Include the cube root of x. We actually talked about that today too, didn't we? So see how it's a lot like x squared? Just how x squared is similar to x cubed on that side. Cube root of x and x and the square root of x are similar to each other on that side. And then what else? I think there was 10. Was there not? You had 1 over x. We did that one today. And let's see. I had him do 1 over x squared. I thought that was important enough to know for a parent function. And just to see the relationship between 1 over x and 1 over x squared. And then I did say 9, but I was thinking there's one more of these that I would do for transformations. All right, well, I found the document where I introduced them last time, and it was just 9. So that's going to be it. So what's the big takeaway from transformations? I guess we already said it all. I just paused, so I kind of forgot what we said. But you got to know your parent functions. That's even more important than transformations, I think. You've got to have a general idea for what all these graphs look like. And, of course, anytime you're actually going to need to know the points on a graph, you're going to just go to a graphing calculator. Transformations and picturing graphs is more about just having a good picture of it in your head before you graph it, like a really quick picture in your head. So I know some teachers will have you like do specific points, or some people prefer to do specific points just because it makes it easier in a step-by-step process. But I think that really does defeat the purpose of transformations. I think transformations are just to think about what is the general shape, where does it start, is it wider, narrower, upside down. That's what's really important with transformations, not getting the specific points that it's at.